Hello everyone and welcome back to the Kohi Game Engine series. Today we're going to talk about transforms. So before we jump into the video, I would like to take a quick minute and thank the partners of the channel. The partners are the highest tier support both on YouTube and Patreon, and they are Caden, Eearslya, Gerboles Inc., Kyla, Super Awesome, and Wensheng. I'd also like to thank all the other fine folks that appear on the screen here. Your support is greatly appreciated. Thank you very much. If you'd like to support the channel and support my work, feel free to have a look at the YouTube membership, or if you prefer Patreon, you can check out patreon.com/TravisVroman. Transforms are probably one of the single most important non-graphical concepts in a game engine because it defines an object's position and orientation and scale in space, and is used for anything that is rendered in the world. And so transforms are a vital concept to get right in a game engine. And so that is what we're going to put in place today because that is the next logical step in our process. The first thing we're going to take a look at is our math types. We are going to introduce a new transform structure. So this is what is going to hold our transformation data. So this defines position, rotation, and scale. Position and scale are both vector 3s. Rotation is a quaternion. We then have a dirty flag, which anytime the position, rotation, or scale are changed, this dirty flag will be set to true. This means that the local matrix that is stored within this transform needs to be updated. That local matrix is right here, which is a mat4. And this is the local transformation matrix, so there's one of these per object in the world. So whenever one of these guys is updated, this guy is recalculated. Finally, in this structure, we have a pointer to a transformation matrix that is the parent. This can be null, meaning the object has no parent, or it can have a parent, which then is used to sort of combine matrices to make sure that the child inherits the parent's transformation. So all of those things are going to be built into our transform for us. One thing that I should mention right now is that you never want to update the position, rotation, or scale on a transform directly by using these properties, because that will not set the dirty flag, and the dirty flag is crucial to making sure that this local matrix gets recalculated. So the way that this is set up, I've put notes on this a lot to illustrate this point, but we basically are going to have functions that we're going to call to update this instead. And so I just want to underscore that point that we should never be updating these things directly unless we also want to set this directly, which is kind of crappy. So a much nicer API would be to just call the functions that we want to update accordingly, and then that will automatically handle the dirty flag. Okay, so that is our math types. Along with that, we have two new files under our math folder. We have our transform.h, which is going to give us our API for creating transforms. So we have a transform create, which creates the transformation with default values. Now, the default values are a 0 position, so x, y, and z are all set to 0. It also includes a identity quaternion rotation, so that is x, y, and z are also 0, and then the w component is set to 1. And then it also includes a default 1 scale, because the default scale of everything is 1. So a transform created by transform create creates it with those default properties. We also have creating a transform from position that takes in a position, pretty self-explanatory stuff. It uses defaults for the ones that it doesn't actually take in, so scale and rotation. We have one to create from rotation, so it uses default position and scale. We also have one that takes in both position and rotation, still creates with a default scale. And then we have one that takes in all three. And basically the way that this works under the hood is all of these above ones call this one, and just pass the appropriate properties to it. So we'll kind of go over that just in a minute when we get into the C file. We also have something here to get the parent, which just returns the parent of the transform that we're pointing to here. So it returns that pointer. We also have set parent, because technically setting the parent can potentially cause us to need to recalculate our matrix. We'll go ahead and have a way to set that here just to kind of keep it as a consistent API as well. Then we have something to get the position, which all of our getters are going to take a constant pointer to the transform and return a copy of what they are actually requesting. So for position, it's going to return a copy of the position. And it's going to take a constant pointer indicating that we are not going to use the value of this, which we couldn't anyways, to modify this because it's a copy, not a pointer. We also have a set here where we take a pointer to the transform that we're going to set the position on, and we take position. And then we also have a translation here. So the difference between set position and translate is set position is an absolute set to the position that's passed here, versus translation, which takes the translation and adds it to the current position. So there's a big difference there in the way that those two work. And there are reasons for having both. So we are going to supply both. Same is true for rotation. So we have a getter, and we have our setter for rotation, and then we also have a transform rotate, which takes a rotation and applies that rotation to the current rotation, versus this that just outright sets it as an absolute rotation. So again, that's the difference there. Scale works exactly the same way. We have a getter, a setter, and a transform scale, which applies the scale to the already existing scale. We also have something to set position and rotation so that we don't have to call those separately. We can just call them in one method and provide both position and rotation. We can also do that with position, rotation, and scale. So we have one method that does that. We also have one that is just translation and just rotation. So again, translation and rotation are applied, not set, to the existing translation or position and rotation. We also have something here that we have a transform get local and a transform get world. So the local basically checks if that internal matrix is up to date, and it checks the dirty flag to say, hey, have any of our properties been updated? If they have, it goes ahead and recalculates that. If not, it goes ahead and just returns it as is. And again, it returns a copy of that, not a pointer to it. Same goes for transform world, only the difference here is it actually gets the local matrix first, and that will automatically handle the dirty flag and all of that. And then it goes ahead and calls the parent if one is actually assigned and gets its local transform and then applies it and returns that matrix. So I'll show you that in just a minute. So in the C file, if we go up here to the top, we can see here that our transform creates, just like I said, calls the set position rotation scale, passing default values, and all of these basically do the same thing, just passing through the appropriate property as we go. Not a whole lot to see here, so all these do is like the set position, sets the position, then marks it dirty. Same thing goes here, so we vector 3 add when we're applying the transform, or the translation rather, set it dirty. We go ahead and do the same for rotation here, same for scale here, and then the same for position rotation, setting it dirty, position rotation scale, setting it dirty, etc., etc., etc. So the one thing we want to note here is our transform get local. This first checks to see if we have a transform that's even passed here. If this is passed as a null pointer, it returns matrix for identity. If there is one that exists, it checks to see if it's dirty. If it is not dirty, it just returns the local matrix. If it is dirty, then it goes ahead and recalculates that and returns the local matrix. So it basically recalculates this by taking the rotation, multiplying that by the position. So it creates a matrix from each one of those, multiplies them together, then makes a matrix for the scale and multiplies that against the transform matrix, and then sets the local to that and unsets the dirty flag, and then returns. So this is where most of the work is done. Our transform get world is also very simple. So it gets the local transform of the transform that's provided here. If that transform has a parent, it gets the world transform of that parent. So this will ensure that it is updated upstream. So basically, whenever we go to if we have a chain of parented objects, this will ensure that the parent checks its parent as well. And then it takes that and multiplies the local by the parent and returns that. If there is no parent, then it just returns the local. If null pointer is passed as our transform, we return a identity matrix. This is purely to ensure that we don't crash the engine from user code or something like that. So that is the transform, and it's pretty straightforward. It's a lot of code, but there's not a whole lot to it, right? Okay, so the next thing we need to look at is back in resource types. So before we had a matrix 4 here for the model matrix. We're not going to use that anymore. We are going to work with transforms now. So now our mesh holds an array of geometries and a transform. One small change that I've made to the geometry system is we've made a geometry system config dispose because we had in our sort of user code the need to clean up the vertex and index arrays. And so we have a check here to see if those things exist and clean them up here, free the memory here. So we can just pass a pointer to the config and do it this way. And this gets all of this logic out of our user code, which makes it less error prone. So I've gone ahead and added this dispose as well for our geometry config. All right, so as with the last several videos, most of our logic actually sits in the application, because that's mostly what needs to be updated at this point. So the first thing that we do is we include our transform.h. We come down here and instead of a D array of meshes, I'm actually going to allocate just on the stack an array of 10 meshes, which would be more than we're actually going to wind up using, just because it's a little bit easier to work with this instead of a D array. Plus, we're also going to have some issues with pointers if we don't do this, and I'll explain that in a minute. So we have our meshes array here, as well as a mesh count instead of a D array. So the first thing that we do within our application create is in our temp, we now set our mesh count to 0. And we go ahead and we create our cube mesh, and we just, instead of creating an empty object, we actually get a pointer to a mesh by taking the address of app state meshes app state mesh count, which right now is going to be 0. We then go ahead and set the cube mesh's geometry count and geometries, do the config, calculate the tangents just as we did before, set the first geometry. All of this stuff is exactly the same. However, we replace the code that was creating the transformation matrix, and we just do transform create and assign that to the cube mesh transform. We then increment the app state mesh count. We perform the exact same process down here by taking the address of the mesh's app state mesh count, which would now be 1. So we go through here, we create the array for the geometries, take the cube config that we generate here, generate the tangents, acquire the geometry from config, set up our transform, which in this case we're actually going to set up a transform from position, and we're going to pass that 1001 position that we were kind of hard coding below. We are also going to call the transform set parent. So we're going to set the cube mesh transform as the cube mesh 2 transforms parent, and this is where that's done. And we increment that count, go ahead and call our new dispose, which I forgot to mention up here. So instead of calling it on these config vertices and config indices arrays directly, we can just now call this single method to clean that up for us. And we're also going to add a third cube. Works the exact same way, it's just a much smaller cube, and it's going to be at a different position, and it's going to be parented to the second cube. So we have this sort of object hierarchy where we have the first cube is the parent to the second cube, which is the parent to the third. So we go ahead and create our third cube that way. And then down here in our application run, we actually change the way our render packet works a little bit. So first off, we start off setting the object to just default, which zeroes out the entire thing. We weren't doing that before, we probably should have been. we go ahead and set the delta time and geometry count as 0, just as we did before. We still are using our D array here. However, we are actually, and I should have mentioned, before I jump into that, let me actually jump back here for a second to our, before I actually do that, let me jump back here for a second and explain the pointer thing that I was talking about. So before, we were actually creating these objects on the stack, and we were copying those into the D array that we had for the app state meshes. And the problem with that is, as soon as we exit this function, we know the pointers that we are actually going to wind up using for the parenting, which is here, become invalid because they were variables that were created on the stack, and they would be destroyed as soon as we actually leave the method. So the reason that we went with an array of meshes within here in the app state instead of a D array is because we want actual pointers to actual still existing and alive meshes. So that is the reason we switched from using a D array there to using an array that is present in the app state, because once we copy that value, or we take a copy of the value, the address is actually different, the pointer becomes invalid, and bad things happen. So that is a quick explanation on that. So back down here into our render packet. So we zero out the packet basically by doing that. We start off with a geometry count of 0, have our D array just as before. We still check to see if we have more than one mesh, or more than 0 meshes rather. We perform a small rotation on the first mesh. So in order to do this, all we do is calculate the rotation just as we did before. That's exactly the same. And then we can say transform rotate. And we just pass in that rotation, pass in the transform, or the address of the transform, and it applies it under the hood. We don't have to worry about any matrix math within here. So this just handles that for us. We also perform a similar rotation on the second mesh if it exists. So we can take this same rotation and just reapply it to the mesh sub1 transform. So that's what we go ahead and do. And then we're also going to do the same thing for the third mesh. So if we have 3 meshes, we're going to go ahead and apply that same rotation to that third mesh as well. So all 3 meshes are going to be rotated, and the code to do so becomes very simple and easy to use. So we still iterate all the meshes, and all of the geometries within each mesh. So that hasn't changed. We still have our geometry data. The only difference here is the geometry still gets the geometries as it did before, but the data.model calls transform get world and passes a pointer passes the address of the transform for the current mesh, which is here. So we take a pointer to that mesh within the array, and then we pass the address of its transform to transform get world. That returns us the model matrix. We push that onto the array, and we increment the counter. Otherwise, this is exactly the same as it worked before. So let's go ahead and, we haven't actually updated our shaders, but I like to post build anyways, just to be sure. I'm going to clean and build. And we're going to go ahead and run. And now we will see a better example of how this parenting works. So we can see, if I go here to a top-down view, we can see here that we have our parent cube spinning, and our offset of our second cube is taking into account the parent's rotation, but it also has its rotation, its own rotation, right? So as the parent spins, it's spinning in position, but it's also spinning on its own. And then the sort of third child cube here is sort of the same thing. So it takes its parent, which is this guy, into account, which takes its parent into account. And then it also has its own rotation. So we can see here that all of this is working as expected. Our texture swapping still works as expected. Our lighting still works as expected. All objects receive light as we would expect. And I'll just go here into the light mode so we can see that happening. So we should be able to see some red get applied to this one. Maybe not on that rotation, but we should be able to see the green get applied there on its way around. Okay, so that is going to do it for this video. We now have a transformation system that's in place that allows us to work with these objects a little bit closer to how we would expect to work with them in any regular game engine. So that's going to do it for this one. Thank you guys so much for watching. If you liked the video, please toss it a thumbs up. If you haven't already, consider subscribing. Those subscriptions really help me out a lot, and I appreciate every one of you guys. And go ahead and click the little bell icon there to get notified as to when new videos in this or the other series that I have going drop, and I will see you guys next time.